Welcome back to The Explainer. Today, we're diving straight into the wild world of AI application security. If you've ever found yourself wondering exactly how developers manage to keep these incredibly smart AI models from doing, well, incredibly dumb or outright dangerous things, you are definitely in the right place. We're going to kick things off by looking at the somewhat messy reality of early AI app development, and then we'll transition into a seriously cool, cutting-edge workflow that's completely changing the game. So let's just jump right in.
19. That is the staggering number of distinct security vulnerabilities that got flagged in a pretty standard AI fitness app during an audit, right before it was supposed to launch. 19 separate issues. And we're talking everything from completely missing authentication all the way up to massive fundamental architectural flaws. When you hear a number like that, it really makes you wonder, just how secure are the AI applications we're blindly trusting every single day?
Which brings us to Section 1, the AI security dilemma, reactive versus proactive. We're going to frame this whole thing as a tale of two completely different projects.
And that takes us to Section 2, Anatomy of an Audit, FitStrat AI. Let's look at that very first case study.
So, FitStrat AI. On paper, it was built on a really solid modern stack. You've got React on the client side, Node.js and Express on the server, and Google's Vertex AI powering the actual Gemini language model. Sounds great, right? Well, the audit testing, which they did iteratively, looking at everything from the NPM dependency graph to static code analysis, uncovered an absolute mess. The critical vulnerabilities basically fell into three buckets: authentication, secret management, and resource exhaustion. Let's unpack exactly what went so incredibly wrong in each of those areas.
The main culprit here was a frankly terrifying architectural oversight. The app's conversational AI assistant was actually firing off calls to Google's Vertex AI directly from the user's browser. Now, because it was built with Vite, the browser tried to grab the API key from a process.env variable. Obviously, that doesn't exist in a browser, so it just defaulted to undefined. But here is the real nightmare scenario. By bypassing the server entirely, there was absolutely zero server-side access control. The app was just sitting wide open.
To plug this massive hole, the development team had to scramble and push out a bunch of reactive fixes. They had to totally reroute all the chat functionality to a secure server endpoint, specifically API/chat, and make sure every single request required an X-app proxy authentication header. On top of that, they realized actual Google Cloud SDK refresh tokens had leaked during development, so they had to immediately rotate those credentials and update their git-ignore files to finally stop secrets from bleeding into version control. If they hadn't caught this, those unauthenticated client-side API calls could have literally resulted in an infinite cloud computing bill.
But as you can probably guess, the dangers didn't just stop at your standard web vulnerabilities. Unconstrained language models are wildly unpredictable. The expected output was, of course, a healthy, personalized fitness plan. The actual risk? The AI could go off the rails and suggest starvation-level diets. And to make matters worse, without a formal response schema in place, the AI was just spitting out totally arbitrary, broken JSON structures that crashed the client-side code entirely.
Now, because this app is dealing directly with human health, strict mitigations weren't just a nice-to-have, they were absolutely critical. The devs had to hard-code strict safety guardrails. We're talking a hard minimum threshold of 1,200 kilocalories for women and 1,500 for men. If the AI generated any number lower than that, the system forcefully overrode it. They also had to set it up to automatically slap medical disclaimers onto every single plan, just to make absolutely sure the AI wouldn't cause any physical harm or trigger a massive legal liability. And what about the actual data the users were putting in? In the first build, they relied on really simple JavaScript truthy checks for user profiles. Because of that, a user could literally type in -999 for their age, and the system would just be like, yep, looks good to me, and accept it. The team had to go back to the drawing board and implement explicit numerical range checks, finite number validations, and super strict JSON response schemas just to keep the data remotely clean.
Finally, FitStrat ran into a major resource exhaustion issue. The application used HTTP streaming and WebSockets for those snappy real-time AI responses, but they forgot to put any limits on the buffer sizes. That meant a bad actor could easily trigger an infinitely large response, causing a total server memory exhaustion attack. Basically, a textbook denial of service. The reactive patch for this was capping HTTP stream chunks at 100 kilobytes and strictly enforcing a 10 megabyte total payload limit. Honestly, it was just an exhausting cycle of constantly patching a sinking ship.
Which brings us to Section 3, a new paradigm, shifting left. Let's completely pivot away from Fitstrat's reactive nightmare and check out a much more modern, elegant solution. The foundational concept we need to talk about here is called shift left security. Basically, instead of trying to desperately patch a leaky ship at the very end of the development cycle, we push all the security measures as far left, as close to the beginning as possible. We're talking about securing the AI app before a single line of code is ever even committed.
Moving into Section 4, Security in 6 Steps, the Anti-Gravity Workflow. For this part, we're going to see what it looks like to build a retail AI shopping assistant in a completely test-driven, locked-down environment.
What is super striking about this specific developer setup is the absolute emphasis on local control. All you need is the anti-gravity IDE, the lightning-fast UV package manager for Python, Git, and a Gemini API key. That is literally it. This entire proactive security lab runs directly on your local machine. You don't need any complex cloud authentication or even a GitHub account to lock down your code right there on your laptop. This workflow secures the entire AI agent lifecycle, straight from code inception down to the final commit. It flows naturally from scaffolding the project to setting a persistent context, running threat modeling, laying down test-driven guardrails, rigorous testing, and finally, those crucial pre-commit scans. Let's zoom in on a few of these steps because they completely flip the script on how AI writes code for us.
Step 2 is honestly revolutionary. You just create a simple text file called context.md right in the root of your project. This file effectively acts as the AI's security constitution. The anti-gravity IDE constantly reads this file in the background while you work, which forces the AI coding assistant to automatically conform to your project's specific secure coding standards. You're basically setting the strict ground rules before the AI is even allowed to think about writing a function.
Next up is Step 3. Here, you trigger a custom AI skill inside the IDE that runs Stride threat modeling. Now, Stride is an acronym that looks for things like spoofing, tampering, and information disclosure. But the cool part is, the AI analyzes your project's architecture for all these threats before any functional logic has even been written. It literally spots the kind of structural flaws that plague the Fitstrat app before they even exist. So, what happens in Step 4 during the planning phase is absolutely crucial. Because of the rules we established earlier, this acts as a hard guardrail. If the AI assistant gets a bit too creative and attempts to suggest an inherently insecure design, like let's say it proposes writing a direct, unparameterized SQL query to a database, the system explicitly blocks that plan. It literally stops bad code from even being drafted.
Once that secure architecture is planned out, Step 5 shifts us into outcome-based security testing. Using Python and PyTest, developers write automated tests to verify exactly how the AI behaves. And these tests are ruthless. They actively try to trick the agent. They verify that our AI shopping assistant actually deflects unauthorized access attempts and successfully blocks malicious SQL prompt injections. If the agent can't protect itself in this test environment, the code does not pass, period.
And that brings us to the final brilliant layer of defense, the local remediation loop. In Step 6, you set up Git pre-commit hooks to run SemGrep, which is a local security scanner. If either you or the AI try to save vulnerable code, that hook stops the commit dead in its tracks. But it doesn't just yell at you and leave you hanging. The anti-gravity IDE actually analyzes the SemGrep report, highlights the exact line of bad code, and suggests a secure fix that you can just review and approve right there on the spot. It's an incredibly smooth process.
So we've journeyed from the totally exhausting reality of retroactively patching 19 separate vulnerabilities in a simple fitness app to a world where our IDE uses AI and incredibly strict guardrails to eliminate threats before a single commit is ever made. But looking at all this really leaves us with a provocative thought to chew on. As AI agents increasingly take over the day-to-day job of writing our code, are we ultimately going to rely on those exact same AI agents to secure it too? It's a fascinating question. Thank you so much for joining me on The Explainer today. Keep learning, keep questioning, and I'll catch you in the next one.